So, hi everyone. In the previous lecture, so far we have discussed a wide range of circuits, and now we are analyzing different opamp based circuits, and so that we understand the functioning of an opamp at a deeper level. Okay, so these are the different set of circuits that we have discussed in the previous lecture, that is so far in the previous 4-5 lectures. And the circuit shown here represent a wide range of mathematical operations, ranging from voltage amplification to unity gain amplifiers to transimpedance amplifiers to adders, subtractors, and integrators and differentiators. So we can perform a wide set of arithmetic operations. So that's what we discussed so far. So to finish the discussion on basic opamp analysis, I had to discuss just one more important point, which is the impedance of the closed loop opamp in the presence of feedback. Okay, so to understand how impedances of an opamp work, it is useful to solve a problem. We can start analyzing a problem like this. This is actually a non-inverting amplifier. I have just added a resistor at the output of the opamp, whose value is say R by 10. And also I've added a resistor between the inverting and non-inverting terminals and at the input terminal as well. So I've added a resistor R at the input terminal and so on. Now, you're supposed to find out what is the output current I0, the output voltage V0, and the input current II. Okay, so previously the circuits that we have analyzed, they didn't have this resistor and this resistor. So if you just look at this circuit here, this one right here is an inverting, non-inverting amplifier. So I just added a resistor here, and then I also added a resistor here, and also one resistor at the output. So that's what I'm showing here. So we want to analyze that. But before we analyze that, I'll take a very simple example, very simple theory. We'll go through a bit of theory. Since you have already done this in other courses, I'm also assuming you must have studied this on your own as well, is what happens to a voltage amplifier in the presence of feedback. A voltage amplifier can be, this part is the voltage amplifier. Okay, without feedback, it is just that you have an input terminal, and I'm going to call the voltage that appears at the input of the voltage amplifier as VD. Okay, and A times VD is the gain of, it's the VCVS model of the amplifier, is the gain of the amplifier with a finite output resistance R out. Okay, and the input resistance of this amplifier is Rn. In open loop, if you don't connect any feedback, if you just remove this feedback and connect this node to ground, in open loop, the input and output resistances are simply Rn and R out. These are the input and output resistances. Now I'm interested in knowing what are the input and output resistances the moment I add negative feedback. Okay, so what I'm doing here, so whenever I add negative feedback, I'm taking a part of the output. So this node be V out, V naught. Beta times V naught is being fed back to the input, such that the total actual input that goes into the amplifier is Vi minus Vf. Right? Instead of the full input Vi appearing across the amplifier, we apply a reduced version of the input, so which is Vi minus V feedback. So now this is a very simple circuit level representation of feedback. In this presence, in the presence of feedback, I'm interested in finding out what happens to the input resistance in closed loop and the output resistance in closed loop. Okay, so that's what I'm interested in. You can derive some very simple mathematical equations. So let's assume for the time being that the feedback network doesn't draw any current, and it also doesn't depend upon any loading. So meaning the feedback network, if you apply a voltage V0 here, the output here is going to be beta V0. It doesn't matter what you connect across this node at this node, at the input and output of the feedback network, it doesn't matter. If you apply V naught here, you will get beta V naught here. That's the assumption. So we can very quickly calculate loop gain. Whenever you're analyzing feedback circuits, it's useful to calculate loop gain. So you can break the loop at this point, and I'll ground. So whenever I break it, since it's a voltage, I have to short this node. I'm making this node voltage 0 and quickly estimate the loop gain of the circuit. Okay. So the loop gain of the circuit, I can go from this node. So if you apply a node voltage Vi here, you will get a Vd here. You will get A times Vd. Then there is a voltage division between R out and RL. Okay. Multiplied by beta. So you are arriving at this point. Okay. So that's what I've written here. This term is the loop gain. There is there is also dependence on voltages here. Vi minus Vf is something that I've written here. So all I'm trying to do is that I want to find out the input and output resistances in the presence of feedback. So this term I'm going to call loop gain as A times RL by RL plus R out. So I'm starting it I'm just trying to come at this point. Starting from this point, I want to come to this point. Okay. So if I ground this node, if I apply a differential volt, if I apply a node voltage Vd across this, you will get A times Vd here, multiplied by this factor. RL by RL plus R out is the voltage at this point. Multiplied by beta, you will get the voltage at this point. So you have returned back to the loop. So this term will be the loop gain of the circuit. I can express, I'll leave that mathematics to you. You can very easily verify that. I can express the feedback voltage in terms of the loop gain as follows. The feedback voltage can be written as loop gain by 1 plus loop gain times Vi. And the output voltage can be written as the V feedback divided by beta. Remember, V feedback, since V naught is simply beta times, Vf is simply beta times V naught. So your V naught is given by V feedback by beta. I'm getting this expression. So finally, I'll write the final results and then I'll show what happens with input impedance. So the difference between the input and the feedback voltage, that is Vd, can be written as Vi by 1 plus loop gain. This is like your error signal. In a feedback system, the error signal of a negatively feedback system is simply given by 1 by 1 plus loop gain times the input signal itself. Okay, so that's just keep this point in mind. So then we can find the input impedances. So now, when you close the loop, the input impedance is simply given by Vi by Ii. In open loop, the input impedance is simply R in itself. But now in the presence of feedback, you want to find what is the ratio of Vi by Ii. Ii is simply given by the input current is simply given by Vd upon Rn. So in this case, it's Vd, the differential voltage upon Rn. And I just derived an expression for Vd. Vd is simply given Vi upon 1 plus loop gain. So substitute that, you'll end up getting an expression. R in closed loop is simply 1 plus loop gain times Rn. That is, in the closed loop, for an ideal voltage amplifier, the loop gain gets boosted by the factor of 1 plus loop gain. Sorry, the input impedance gets boosted by a factor of 1 plus loop gain. So if loop gain tends to infinity, then the input impedance will also tend to infinity. Okay. So this is some very useful point to keep in mind, which means what will be the value of Ii if your loop gain tends to infinity? Even if you have finite Rn, what do you think will be the value of Ii? Are you able to hear me? What do you think? Yeah, the value of Ii will be 0. Now, I've already discussed mathematical intuitions. Can you guess intuitively why should Ii be 0? I mean, of course, we can derive mathematical equations and prove that Rn is 1 plus A beta times this. But can you use intuitions and say that, can I use this very simple logic? that it doesn't matter what the input impedance is. If your forward path gain, if A tends to infinity, let's assume A tends to infinity for any finite output V naught. If V naught is finite, or I can say this node is also finite. If you want A times VD to be finite, what should happen to VD? So if A tends to infinity, I want this voltage to be finite. Let's call this VO1. This I'm going to call this node as VO1. Your VD is simply given by VO1 upon A. If A tends to infinity, then VD tends to 0. Okay? So the intuition tells you that the differential voltage has to go to 0 if your forward path gain is infinity. That means this node voltage and this node voltage will become equal. It doesn't matter. It doesn't matter if you have finite resistance or not. If A tends to infinity, for you to have a finite output voltage, VD has to go to 0. So therefore, this node voltage and this node voltage will come to the same values. Therefore, II has to be 0. Okay? So that's the intuition behind it. So now if I go back to this circuit, immediately look at this. This is the op-amp. It is a negative feedback. There is no doubt about that. You are taking the output signal and feeding it back to the negative terminal. Since you are feeding it back to the negative terminal, now I'm interested in finding out what will happen to these two node voltages. If A is infinity, since the circuit is a negative feedback, we can assume that the output is going to be some finite value. If the output is finite and the open loop gain is infinity, then V plus has to become equal to V minus. It doesn't matter, even if you connect a resistor in between, this condition has to hold true. So the inverting and the non-inverting terminal voltages will follow each other. If that happens, what will be the current flowing from the input? What do you think will be the current drawn from the input now for this amplifier? Here, 0 current, right? So because these two node voltages are same, this node voltage and this node voltage are same, no current flows through the resistor. So I can ignore this. If no current is flowing through the resistor and op-amp's input is not drawing any current, because the input of an op-amp again is ideal op-amp, it doesn't draw any current. So therefore, this current will also be 0. You're not drawing any input current at all. So I might as well ignore this resistor as well and treat it like a simple, I can remove all the resistors. The resistors really don't have any role because no current is flowing through them. Okay, so this node voltage comes to Vi. So can you tell me now what will be V naught? What will be V naught now? Does this resistance have any role to play? I'm measuring the voltage at this point. Remember, I'm measuring the voltage at this point. So what part of the voltage is fed back? The fed back voltage is simply V naught by 2. So this node, the fed back voltage is simply equal to V naught by 2. Right? It's a potential divider, R and R, you get V naught by 2. That should be equal to Vi because of negative feedback. V plus will be equal to V minus. You get V naught as 2Vi. Okay, so that's the voltage gain of a non-inverting amplifier with two equal resistors in the feedback and the input and the not inverting terminal. Okay, that's just 1 plus R2 by R1. So 1 plus R by R is 2. So all I'm trying to say is that this circuit, even if we had resistances here, it didn't matter at all. II is 0 and V naught is simply equal to 2 times Vi. So can you tell me what will be I naught, the current I naught here? What will be the current that the op-amp has to supply? We just analyze the circuit. What do you think the current I naught has to be? This node is at Vi. If this node is at Vi, the current flowing through the resistor is Vi by R. Now, why is everyone saying 2 there? Where is 2 coming into the picture? See, this current flowing in this resistor is, see, this node is at Vi by R. So, see, you can look at it. I'll give you the explanation. I think I understand where the confusion. Everyone's saying it's Vi by 2R. Someone is saying 2 Vi by R. So let me give an explanation. So this node voltage comes to Vi, right? So because that follows from II is 0. So this node is at Vi, this node is at Vi. So the current flowing through this resistor is Vi by R. And that current has to flow through this resistor as well. So the current flowing through this resistor is Vi by R. That current has to flow from here, which is same as I naught. So I naught equals Vi by R. You can also look at it this way. Let me redraw the circuit a bit so that you understand it in a more intuitive way. I can also look at the circuit this way. So let's say this is R and this is R. We just analyze the value of V naught equals 2 Vi. Now the entire voltage across these series resistors, 2 series resistors is 2 Vi. And that series resistance is 2R because no current flows through this node. It's 2R. So I can say 2 Vi by 2R equals Vi by R. So I naught equals Vi by R. The current that the op-amp has to supply also doesn't change. It doesn't depend upon the output resistance. Any resistance I add here, bit from the output of the op-amp to the output node, from where I'm taking the feedback, this resistance really doesn't come into play. Okay, I naught is simply Vi by R. I naught is the current through this resistor. Now, what is this node voltage? The op-amp's output itself. What happened to the op-amp's output? If I call this node be VO1, what is the voltage at VO1? What is the node voltage of op-amp's output? No. See, this node is at 2 Vi. This node is 2 Vi. So what should be the output of the op-amp? It should be 2 Vi plus the voltage drop across the resistor. And what is the voltage drop across the resistor? So it's R by 10 is the resistance value. And the current flowing through the resistor is Vi by R. So it will be Vi by 10. So if this node voltage is at 2I, VO1 is going to be 2 Vi plus 0.1 Vi. So that will be 2.1 Vi.
Sir, didn't you say that the R by 10 won't come into play?
Yeah, it won't come into play at this point. At this point, too. I mean, it won't impact your. See, let's say I don't have R by 10, and I just short this node. The current I naught will remain. The current that the op-amp has to supply will remain the same. And the output, the voltage V naught will remain the same. Okay. But adding R by 10 will change the absolute op-amp's output voltage. I mean, the output of the op-amp itself will change, but not the output voltage. Because it's carrying some current. So that the op-amp's output node has to change. That's the only change. Yeah. What I meant was if you look at the circuit as a black box, if you include R naught as R out as a part of the op-amp, then it doesn't change. Okay. But I'm here asking a voltage of an internal node. Okay, here the output of the op-amp happens to be an internal node. So that's why it's changing.
Understood, sir.
Yeah. So this node voltage here will be 2.1 Vi. Okay, guys, I'll move on to the next question. So this is a very useful problem which tests your understanding of input and output resistances of an op-amp. So if you have any doubts, ask me now, and I'll move on to the next problem. Okay, it was clear, right? So all I'm trying to say is if you add a resistor in between, it really doesn't matter. Okay, if you have the op-amp to be ideal, if this op-amp is ideal, it doesn't matter at all. So even if I put a capacitor here, it shouldn't make any difference. If I ask you what is the current flowing through the capacitor, that will also be zero. So any resistance I connect between the two terminals shouldn't matter. So let me show you a different problem. So let me ask this question. Now, can you tell me, this is an inverting amplifier, okay? An inverting amplifier. I am interested in finding out, I'm interested in knowing what will be the current drawn from the input II, what will be the current supplied by the op-amp I0, the output voltage V0, and the output of op-amp VO1. So can you guys solve this? Use all the same ideas that we have discussed so far. You have to use all your understanding of a basics of an op-amp circuit. So yeah, use all that and try solving this one. So first check, is it a negative feedback? So so this II is VI by R, that's correct. So first step, what the current flowing through the op-amp is zero. You're looking at the input terminal. Op-amp doesn't draw any current through at the input terminal. So I've assumed that to be zero. If that current is zero, the resistor drop, voltage across resistor is zero. So I might as well short circuit this. The other node is connected to ground. So the voltage is zero. So this node is at 0 volts. Since the op-amp is in negative feedback mode, and the forward path gain is infinite, it's an ideal op-amp with an infinite gain, this node will be also at 0 volts. If this is at 0 volts, no current will flow through this resistor also. This resistor doesn't really matter. So I can remove the resistor, and yes, treat this node voltage is at ground. This is at 0 volts. So therefore, the current flowing through the input resistor is simply VI by R. II is simply given by VI by R. So if II is VI by R, that current has to flow entirely through this resistor. Okay. And the voltage drop across the resistor will be VI in this direction. So if I'm measuring the voltage at this point, what will be V0 now in terms of VI? This node is at 0 volts. Voltage drop across this resistor is VI. It will be minus VI. V0 is minus VI. V0 is simply equal to minus VI. Now, if V0 is minus VI, what is I0? What is the current supplied by the op-amp? Remember, I keep the direction of current in mind. I'm showing it as the current being supplied by the op-amp. Keep the direction of current in mind. So the current that is being supplied is VI by R, right? So VI by R is the current that's flowing through this resistor. That's flowing through this resistor as well, and that has to flow here as well. So the current that's being supplied by the op-amp is minus of VI by R. I'm just maintaining the polarity. The directions I'm keeping in mind because I'm treating it as current supplied by the op-amp. Since it is negative, what does it mean? It simply means that op-amp is sinking that current. Okay. Instead of supplying that current, it is sinking that current. So op-amp is drawing drawing that current inside. So I can say that current so this current II is flowing through this into the op-amp. That's what's happening. Okay. So what will be the output voltage V0 is simply minus Vi. And what is the output voltage of the op-amp? What is the voltage at the output of the op-amp? So this node voltage, yes. So if this node voltage is minus Vi and you have a current that is flowing in this direction, okay. So the voltage at this point is going to be minus 2 Vi. Okay. Is it minus 2 Vi or 0? Yeah, it's minus 2 Vi. Okay, so this node voltage is, you can look at it this way, it is plus. So this node voltage is Vi volts lower than, because the current is flowing in this direction. The op-amp's output VO1 is Vi volts lower than output. So it is V0 minus Vi, so which is minus 2 Vi. That's it. So that's something for you guys to keep in mind. I just wanted to discuss that one problem alone. Now, the second question that we'll discuss for today is a very interesting application. Let's say we have a source with a finite source resistance. Okay, so generally the source resistance, if I model a source resistance with a voltage source, it usually means that, so generally, even if you look at batteries, your the AA, AAA, AA batteries, they will all have a maximum current rating. I mean, they will usually have a maximum power rating, how much power they can supply and all that. Okay, so usually that tells you the maximum power that the device can provide, or maximum current that the device can provide. So here, the maximum power is often captured by modeling a resistance in series, a resistor in series with a voltage source. Now, you guys have already studied a theorem called the maximum power transfer theorem in your basic electrical sciences course. So can you tell me, if you connect a load resistor across this battery, I mean, let's call this as voltage source with a finite source resistance, a finite power source, what is the maximum power that you can deliver to RL, the load resistance RL? What is the maximum power that you can deliver to the load resistance RL? Not 50%, express it in terms of Vs and all that. So look at it this way. When under what conditions, under what value of RL will maximum power be transferred? Can I say RL should be equal to Rs? Right? That's the condition under which maximum power is transferred. So if RL equals Rs, then the voltage across the load resistance has to be Vs by 2. Right? So if RL equals Rs, it's a potential divider, Vs by 2. So V square by RL. So Vs square upon 1 by Rs, that's equal to Vs square by 4 Rs. This is the maximum power you can deliver to a load resistance. And that is modeled by your source resistance. So if you have a very high source resistance, okay, then it simply means that you can deliver very low power. So which normally happens, when, especially that's why you put amplifiers. Usually circuits called microphones, they generate very low powers. Okay, so then you normally put amplifiers to boost their signal levels, power levels, power delivering capacity. So now the maximum power that you can deliver is limited by the source resistance. Now, what I'm going to do is that I'm just going to break this point. Instead of directly applying the voltage source to the load resistance, I'm going to use an opamp in a voltage follower mode and then feed it to the load resistance. Now I'm interested in finding out what is the output node voltage. So if I ask you what is the output node voltage, what will that be? What will be the value of V0 in terms of Vs? Since the input current drawn is 0, I can assume that this node voltage will be Vs. If this node voltage is Vs, op-amp is a negative feedback. This is also at Vs. So your V0 will be equal to Vs. Now, what is the maximum power that you can deliver to the load? What is the maximum power? See, don't worry about AC, DC and all that, okay? I'm just interested in maximum power. It is simply Vs square. This is the instantaneous power. Vs square by R. So it will be Vs square by RL. So the maximum power that you can deliver now becomes equal to Vs square by Rs. Previously, it was how much? Vs square by 4Rs. Okay, you cannot, there was a finite number. You could never exceed this number previously when I had directly connected the voltage source to the resistor. But now, if I use an op-amp, it turns out the maximum power you can deliver is Vs square by RL. If I make RL 0, that maximum power I can deliver tends to infinity. Okay, the maximum power that I can deliver actually blows up to infinity. And all that is happening because of the op-amp. The op-amp is now, since the op-amp is now supplying the current. Previously, the voltage source was supplying current to the load resistance. But now op-amp is supplying the current. So this is one example. You might wonder, why would I need a voltage follower, right? It's just a unity gain amplifier. Why would I need it? I need it in applications where I have to deliver a power to the load and your input source happens to be a very poor quality input source, meaning its source resistance is high or it cannot deliver high powers. If it can't deliver high powers, then you can just insert a voltage buffer in between. This is also called a voltage buffer or a voltage follower in between the source and the load. Now the buffer will determine how much power you can deliver to the load resistance. The maximum power that you can deliver to the load resistance is now dependent on the buffer. And buffers generally will have much higher power handling capacities. To better understand this, if I, for example, I can say, okay, why not draw a Thevenin equivalent for the circuit and see what happens? Once I add, I'm interested in drawing the Thevenin equivalent of the circuit. So how do you draw Thevenin equivalent? First, open circuit. Just remove the load and measure that node voltage. So I can take this part of the circuit and try to find out what is the open circuit voltage for this circuit. If I ask you what is this node voltage, what will that be? That will be Vs itself, right? There is no change there. That will just be Vs itself. Now, the next thing I'm interested in finding out is this output impedance. How do you measure that? Short circuit your input and apply a test voltage source and measure the current that's being drawn. So I'll remove this. The open circuit voltage we just found out to be Vs. Okay. I want to find the test voltage source and I'm interested in finding this. Or I said, whenever your input impedances are lower, always use current sources. Let's say I inject a current source of value I test, IT, and I'm interested in measuring the voltage here. What is the voltage here? Input signal is 0. This is now at 0. What will be the voltage at this point? This node is at 0. Positive terminal is at 0. Negative will also, because it's negative feedback, this is also at 0. So this node will go to 0. And this follows directly from the virtual ground, the concept of virtual ground. If I grounded my positive terminal, negative terminal should also follow the positive terminal, right? So therefore, it's like a virtual ground. Because I'm injecting a finite current and the node voltage tends to be 0, I can say that Vt by It equals to 0, which is the impedance is 0. So the Thevenin resistance is 0. So if I model this, the Thevenin voltage is Vs itself, but the Thevenin resistance, let's call it RSTH, is the Thevenin resistance is 0. This is the equivalent circuit of the buffer. This is what the op-amp is doing to you. It's actually, in effect, it's transferring the same voltage, but at a much lower source impedance. Okay, so it's almost transforming the source for you. Okay, so that its power handling capacity is greatly amplified. I just use the word, I'm just saying it simply means that I've just decreased its source resistance. I've just transformed its source resistance. I've maintained the same voltage, but the source resistance is greatly reduced. Okay. Now the next problem, this one is based on integrators. And here again, I'm applying a step input. So you guys should know that if I take a step input and integrate it, that will be just a ramp. That's the basics you have to know. Now, what I'm interested in is that this is an op-amp with a saturating nonlinearity, meaning the output cannot go greater than, less than, plus minus Vsat. It cannot exceed these two voltages. Okay. It cannot exceed plus minus Vsat. Now I'm interested in finding out what happens to the circuit in real time at this output as I apply a step input, a sudden step input. So can you plot the waveform V0 as a function of time? So first, this is an inverting integrator. So the characteristics in Laplacian domain V0 by Vi is minus 1 by SRC. I will also ask you to assume that the initial voltage V0 of 0 is 0. Initially, the capacitor is discharged, so there is no voltage across it. Now I'm suddenly at t equal to 0, I'm applying a step input, a unit step input, 0 to 1. In time domain, I can write V0 of t as minus 1 by RC integral Vi of t dt. So it will be 0 to t, right? The input is 0, input is 0 before t equal to 0. So this is what you get. So if I substitute 1, all I'm going to get is minus of t upon RC. If I substitute Vi equal to 1, because it's a step input. So for t greater than 0, I'm going to get an output like this. For t less than 0, it is 0. So how it's going to look like? It's going to look like I'm plotting your output starting at t equal to 0. It will be a ramp function. It will keep on be a negative ramp because its output is changing. At what time instance do you think it will reach Vsat? It should be roughly Vsat times RC. Okay. As you keep increasing, so when this node voltage, when T by RC becomes equal to minus Vsat, at that point, your op-amp starts saturating. Then your output flattens out. So it reaches minus Vsat. And what is the time instance at which it happens? You can find that by equating minus T by RC to minus Vsat. Okay, it is RC times Vsat. So remember, T by RC is actually a dimensionless quantity. And this, because the voltage, for example, I can probably assume like this. I can assume that instead of 1 volt, if I say the step voltage is some Vs, V capital S, okay? Capital Vs is the step voltage. Then this node voltage will be times Vs. I should substitute Vi as Vs and integrate it. So then you will get the time as times Vs. So the time at which you reach the saturation voltage is given by RC into Vsat by Vs. This is the result you get. So if Vs equals to 1 volt, you will get Vsat into RC. So this time instant where at which your output starts saturating is RC into Vsat upon Vs, where Vs is the step voltage level. So can you tell me what happens to I naught? What we have plotted is V naught. What about I naught? If I ask you to plot I naught, how do you think it will look like? Look at the direction of current. I naught is in this direction. I naught will be constant. So that's right. So I'm assuming that the op amp is going to be in negative feedback. So see, again, I'm making some assumption here. The assumption is that the loop gain is so high, the op amp's loop gain is so high, that I'm going to assume that your circuit is still in negative feedback. There is a small catch here. We'll revisit that later. Okay. Whether is it in negative feedback or not, I'll come back to that later. But right now you can assume that it's in negative feedback. So if this is 0, the current that's going to flow is VI by R, Vs by R. That current flows through the capacitor constantly, a constant current, and that is being taken in by the op amp. So the current I naught is simply given by Vs by R. It will be a step current. Will it be a step current always? What will happen once the op amp's output saturates? Once your op amp output saturates, what happens? I just said that the loop gain goes to 0, right? Because once your op amp output saturate, then there is no gain in the circuit. Your output is not changing. If your op amp's output saturates, it's constant at Vsat, which means you are pushing the current, but this node voltage V0 is not changing. It is staying put at what? Minus Vsat. So it is staying at minus Vsat. So you will have a situation like this. Look at this input. Op amp is no longer in feedback, so I can forget about op amp. So you'll have a situation like this. You'll have a resistor, a capacitor, whose one side of the capacitor is at minus of Vsat. The other side, initially it was at 0 volts. This will be R. This node is at Vs, a DC voltage source of Vs. Now, what do you think will happen? Will it immediately come to 0? The time instant at which this is happening, RC into Vsat upon Vs. Will it immediately come to 0? That's right. Capacitor will discharge. So one of you said capacitor will discharge. So what will happen? Let's analyze a simple RC circuit like this. So if you have a RC circuit with some initially assume that 0 charge, if I apply a step input or if I apply a DC input of voltage Vs, the capacitor will start charging. Okay, the capacitor will start charging until the cap voltage reaches Vs. It will keep on charging. It will keep on charging as long as there is potential difference between these two nodes. The resistor will generate a current and it will keep charging the cap. Once the capacitor reaches Vs, it will stop charging. So that's what is going to happen here. So you will keep on the output node voltage will stay put at minus Vsat. But this node, the capacitor's node, this I'm calling it this node as Bx. Your resistor will start pushing current into this capacitor. Yes. So a capacitor will undergo this charging happens. So whenever you have, it's like a first order resistor and capacitor. When you have a first order resistor and capacitor, then this, as far as the RC circuit is concerned, this R and C is concerned, suddenly it will look like I have applied an input Vs. Now opamp is no longer in the play, is no longer in the circuit. This will look like an RC circuit with a step input of value Vs. And you can treat that the capacitor is initially charged to a voltage of minus Vsat. Okay, or you can just leave it like this. You can just assume I'm applying a node voltage plus Vs here. This node voltage is at minus Vsat. Okay, so this node voltage, it will keep on, the resistor will keep on transferring charge to the capacitor till this node voltage reaches plus Vs. So that the total voltage across the capacitor, it's going to be minus Vsat minus Vs. Okay, so this node voltage will come to Vs. The other node voltage is staying at minus Vsat. And it will be an exponential. I mean, the first order RC circuit. So for a first order RC circuit, the voltage across the capacitor, if you assume that this node voltage is, if you ignore minus Vsat, we can apply principle of superposition and say that this happens. Okay. So keep in mind, the opamp is maintaining this node, even if input is changing. Because now remember the opamp, the job of the opamp, you are charging this node. This node is going through a positive voltage. Because this node is positive, the opamp is no longer in negative feedback. Therefore, V plus will not be equal to V minus. Once the output reaches the saturating voltage, this condition will not hold true anymore. V plus will not be equal to V minus. So this guy will be increasing in voltage and the output will stay put at minus Vsat because the opamp is now in the saturating point. It's in this point. Your V plus, the differential voltage across the opamp is, the differential voltage across the opamp is negative. So opamp's output, the capacitor, this node voltage will forcibly, opamp is forcing that to stay at minus Vsat. And the resistor will keep on supplying current until this node voltage goes to Vs. That's it. So the current that the opamp is supplying will start at, initially it was at Vs by Rs. Then it will slowly keep decreasing. It will go to zero. It will be an exponential discharge and it will go to zero. Eventually, it will be an exponential discharge with a time constant of Rc. And the node voltage, the inverting terminal V minus, I called it as, let me erase all this. Okay, so this node voltage, if I plot Vx, this node voltage was constant. It was starting from 0 till Rc Vsat by Vs. It was always 0. Then after the opamp's output starts saturating, this guy will go through a first order rise and it will reach a value of Vs. And the current that the opamp is supplying, it goes from, I'm actually, probably I should draw a different sign. The current, since I've shown the current to be in this direction, it should be negative polarity. So let me show it this way. So if I draw from t equal to 0, this is time. The current will initially be Vi by R minus Vs by Rs till you reach this point. After that, it will discharge, it will eventually go to 0. So this is minus Vs by R. The current that the op-amp's output supplying will eventually go to 0. And the voltage across the capacitor will eventually be, you can do that. It's the positive voltage will be Vs plus Vsat. That's the voltage across the capacitor. Yeah, you can calculate it. If I ask you what is the total charge stored in the capacitor, until t equal to 0, it reaches at this point. When you reach the saturation voltage, it will be Vsat into C. After that, it will become Vsat plus Vs into C. Remember, because your capacitor is always getting charge, right? It's always getting charge in this direction. This guy is always supplying current, only in one direction. So the cap will keep on adding more and more and more and more charge. Okay. Output will stay at minus Vsat, but this node voltage will be at plus Vs. Okay. The concept of virtual ground doesn't hold anymore once op-amp's output starts to saturate. Okay. So I used 2 to 3 different ideas here. First order charging, the concept of first order charging, and of course, the idea of basic integration and saturating nonlinearity of the op-amp. Okay. The only thing you have to understand here is first order charging, right? So if you have a resistor and a capacitor like this, if you apply a step input going from 0 to Vs, the capacitor voltage will start rising from 0 till Vs. In a exponentially, it will rise. Okay. It's asymptotically, it will rise. And the current flowing in the circuit, if I ask you what is the current flowing in the circuit, it will start from Vs by Rs and eventually go to 0. Once the capacitor is fully charged to Vs, the current in the circuit will come to 0. Okay, that's the charging. That's what happens in a first order RC circuit. And this circuit, the integrator, does not behave like a first order RC circuit till the op-amp goes out of saturation. Okay, op-amp is pushed to saturation. Once the op-amp is pushed to saturation, then it doesn't matter. The op-amp is no longer in play. After that, it starts behaving like a first order charging. So that's why you see this behavior. Okay. So this is a very useful problem to keep in mind. So I'll move on to the next question. If you have any doubts, you can ask me now in this one. Is that fine? You want me to explain anything here, or is that clear?
It's clear, sir.
Yeah, okay. Thank you. So the next one, this is again a very useful circuit, an integrator with a saturating output. And you will encounter such circuits later when we talk about function generators, because now that you're using different instruments in the lab, you'd be using an instrument called function generator, which will generate sinusoids. If you can pick the different waveforms you want from a menu, you can generate a sinusoid, you can generate a ramp or a sawtooth waveform, you can generate a square wave. Okay, so I just want to illustrate one simple example. So we'll take a very simple example here. I'm feeding a square wave signal which goes from +1 to -1, +1 to -1 like this, to a integrator circuit. And I'm interested in finding out what is the node voltage at this point. And the output stays, the input signal stays at +1 for t seconds and -1 for t seconds. And it is given that the t, the on time here or off time, equals RC. Assuming that the input voltage, the initial voltage across the capacitor is 0, which means output voltage is initially 0. Okay, you can again assume that the op-amp is in actually negative feedback mode. Starting from -1, your input signal is going to start from -1. Suddenly it starts from -1 and it goes to +1. I want you to plot what will be the output waveform. Can you try this out? So this is -1, this is +1. So let's start from here. If you start from here, you just have to integrate this waveform. If you integrate this, what do you get? So integral 0 to t, 1 over RC, Vi is 1 volt dt with a minus sign. It's an inverting integrator. So you get minus t by RC. So it will slowly start discharging at the end of t seconds. At the end of, you are applying +1. Yeah. So if you are applying +1, its output will start from 0 and it will start discharging. The output will go negative. I'm sorry for using the word discharging. The output node will go negative. When t becomes equal to capital T, since I said this condition t equals RC, you get -1 volts. So at this point, you will reach -1. The op-amp's output will reach -1. Now, the op-amp's output is at -1 volts. Immediately, the input flips its polarity. It was initially +1. Suddenly, now input becomes -1. So previously, if you are pushing current in one direction, now you are pushing the current in the opposite direction. So what do you think will be the output? What will happen to the output? Will it increase or decrease? So you can take a much simpler example. Assume that I have a capacitor like this. I'm just pushing a current. Initially, the current is positive. If I push a positive current into a capacitor for t seconds, the voltage across the capacitor will increase to some value. Let's call I0 and minus I0. So if the capacitor value is C, it's going to be I0 by C into T. T is the on time. So this value that it will reach is I0 upon C into T. Once it reaches this value, and suddenly I'm flipping the polarity of the current. I'm injecting a current source, a pulsed current source here. This is I0 and this is minus I0. If I do this, I'm flipping the polarity of the current. In one cycle, you are charging the capacitor. In the other cycle, you are discharging you are removing current charge from the capacitor. So now what happens? When you come to this point, remember the slope is same, but your starting point will be different. You will start from here, you will remove the charge from the capacitor. So you took t seconds. You took t seconds to build a certain amount of charge. And if I pull out the same current for t seconds, you will remove all the charge that you supplied. So you will come back to 0. And it will continue like this. So it will be a ramp waveform, a sawtooth waveform that looks like this. If I just apply a pulsed current to a capacitor. The same thing will happen here as well. See, this current source, this resistor here, the voltage across the resistor is simply given by Vs itself, the input voltage. Whatever the input voltage is here, that's the voltage across the resistor. Okay, that's the voltage always. That's the volt. As long as your op-amp is within plus minus Vsat, output is between plus minus Vsat, which I'm going to assume is true in this case. The voltage across the resistor is always constant, which means the current to the resistor is also fixed. That is simply given by Vs by R. So I can remove the resistor, I can remove the resistor and replace it by a current source whose value is given by Vs by R. And what is the current source waveform? If voltage goes from +1 and -1, the current source will go from 1 by R and -1 by R. So now this current is flowing through this capacitor and into the op-amp. So now you can see the same thing is happening. What was happening here, I showed an example of a current source charging and discharging a capacitor. The same thing will happen here too. A pulsed current source whose polarity is changing. One's positive, one's negative. For t seconds it is positive, and t seconds it's negative. So your voltage will also keep going. It will start from 0. Initially, I'm assuming 0 volts initially. It will go to -1. And then for the remaining, the next cycle, it will go to this. Why is this? Because the current that is discharging is also of same magnitude. The current magnitude is same. So if I let the current be on for t seconds, whatever charge it supplied in the positive half cycle, it is going to remove all the charge in the negative half cycle. So it will come back to 0 volts. The capacitor charge, whatever it supplied here in this positive half cycle, will be taken out in the negative half cycle. So that's what will happen. So your output waveform will go from 0 to -1, 0 to -1, and so on. So now you have converted a pulse signal to a sawtooth waveform. So this is how you do it. If you can generate a pulse signal, then you can convert that pulse signal to a sawtooth wave, a triangular waveform. So something like this, your function generator will have an internal circuitry that looks something not exactly the same, but the idea is somewhat similar. You start with a pulse, convert it to a triangular. Now, how do you get that pulse? So again, there are circuits for that. We'll discuss it at a later stage. Okay. So if you apply a pulse signal, you'd get a ramp output like this. So this is the last circuit. We'll analyze this and then I'll open up for doubt sessions. So I have shown a circuit which is a inverting amplifier. Okay. So, okay, one of you asked a question. Can you draw a case where the output saturates? See, we have analyzed what happens when output saturates when you apply a fixed input. A similar thing will happen here too. Let me finish this problem and come back to that. So it's not very difficult. So what will happen is you will no longer, the output will not increase like a ramp anymore. It will start from 0. Let's assume your slope is so high. It will reach VSAT. And even though the current is trying to charge, the output will not change. It will always stay at minus VSAT. Once your current changes its polarity, so I'll come to that because it requires some understanding of negative feedback. Probably I'll discuss that in the next class because it takes some time to digest what happens when you suddenly flip the polarity. The op-amp is now in saturation. Suddenly it has to come back to a negative feedback mode. So it transitions from one state to another. So that requires some thinking. So probably I'll discuss next, probably in the next class. Okay. So I'll come back to this circuit here. Can you quickly analyze and tell me what will be V0, I0, and II, the input current for the circuit? We have already done this. Can you say what will it be? What will be V0 in terms of VI? Let's call this VI. What is V0 in terms of VI? Minus Vi, right? That's correct. minus Vi. This node is at 0 because no current flows through this. So even if you connect some impedance here, it doesn't matter. So this node is at 0. If this node is at 0, then this impedance doesn't matter. Whatever you connect here, any current that's going to flow here will flow through this. So this impedance doesn't matter. Okay, even if I connect RC, whatever impedance, it really doesn't matter. So I can remove this. I can remove this. I can treat this as ground. I can just treat this as ground. And that will be V naught equals minus Vi. It's an inverting amplifier with a gain of -1. Now, what is II? II is simply Vi by R. That's always the same. There is no change there. What is I naught? If I ask you, what is I naught? What will be your answer? What will be I naught? See, if there was no resistor here, if let's say RC did not exist, if RC did not exist, if then the current Vi by R has to flow through the opamp. So I naught will simply be equal to minus of Vi by R. There is no confusion there. But the moment I put a load impedance here, the current flowing through this load resistance is given by V naught by ZL. Because that current has to, I mean, if the moment you add a load, it is also going to consume some current. That's going to be V naught by ZL. That current also has to come from opamp because the current through this resistor is fixed. This resistor current is fixed. So therefore, I naught is going to be equal to, let's call this current as IR. Let's call this current as, So let's call this current as IL. That's the current to the load resistance. So if you apply KCL at this node, your output current is going to be minus IR plus IL. Minus IR is simply minus of Vi by R plus V naught by ZL. Since V naught equals minus Vi, I can write it as minus of Vi into 1 by R plus 1 by ZL, or simply I can write it as minus of Vi by R parallel ZL. Where keep in mind this resistance R is what? This resistance here. So even if I make this resistance, for example, if I make this resistance 10R, the current flowing through the resistor will not change. This IR will not change. This current as IR, the current that is flowing through this resistor, is only determined by the input resistance. Okay, that doesn't change. But the load current will change because your load voltage has increased. Your V naught has increased. Because your V naught has increased, you have to now supply more current to the load resistance. And that more current will come from the opamp itself. Okay, so I'll revert it back to R. So I'm just wanting you to keep in mind that the R that I'm writing here is actually, I'm writing it as minus Vi by R. This R is the input resistance at the input terminal. Then plus V naught upon ZL. The opamp has to supply two currents, this current and this current. Right? The moment you connect load resistance, it's going to demand some current. And because it's a voltage amplifier, all that current will come from the opamp itself. Opamp will supply all that current. Okay, so that's it. Yeah, that's it for today. I'll stop recording. You can ask.